So these notes will match the 9-1 reflection notes that you have to fill out. Some goals for this lesson: you are going to be drawing reflections in the coordinate plane, calculating any sort of reflectional change with coordinates. So that means we'll be calculating the image coordinates based on the reflection. We're going to derive some formulas for reflecting over the axes, so those will be some shortcuts. And then there'll be a challenge at the end to write an equation of a line of reflection. You'll notice the do now on your notes talks about a paper battleship game. If we haven't discussed that game yet in class, just ignore the do now and move on to this box titled reflections. This is the definition we're going to work off of. It's a function, a transformation, matching each preimage to an image opposite the line of reflection. So that means there will be equal distance on either side of the line of reflection, and the line connecting each pre-image to its image will be perpendicular to the line of reflection. The points on the line of reflection, as you can see, like this red letter or this red point here, that point is unaffected by the reflection. What's really the most important is that the line of reflection is the perpendicular bisector of the segment connecting points and primes. So to elaborate on that, if we look over here at the image on the right in your notes, A to A prime is a line segment. K is the line of reflection. K cuts directly through the middle of that line segment, creates a 90-degree angle, and bisects the line. So because it bisects the line and creates a 90-degree angle, we call it the perpendicular bisector. First example is going to be to reflect the triangle in the line x equals -4. Remembering which lines are horizontal and vertical was one of the things we talked about at the start of this unit. X equals -4 is a vertical line. It's going to be at the point x equals -4 and will be vertical. So go ahead and graph this line. Now we want to count how many spaces is each point away from the line. Well, if we count, J is 4 points to the line, L is 2, K is 2. The directions matter as well, because when we reflect, we want each point to end up on the other side of the line of reflection, but it should be the same distance away. The line of reflection has to bisect the point and its prime. So we duplicate that distance in the opposite direction, or continuing in that same direction, the opposite side of the line. And we connect the points to get our shape. The shapes are identical. That makes it something called a rigid motion transformation, meaning the preimage and the image are congruent. Example 2, you can pause this, try it on your own. You can draw it. Do the same steps. Find the distance, duplicate the distance on the other side of the line of reflection, and see where your points end up. Y equals 2 is a horizontal line, so your line should look like this at the point y equals 2. Find one distance, duplicate it on the other side. Your image should look something like this when you're done. Here's the kicker. What if there's no graph? Well, we're going to do some calculating with the coordinates. These are the coordinates we had for the first triangle, I believe. We're going to reflect across the line x equals -4, but we have to figure out what's the distance away from x equals -4. Because we're working with x equals, that means only the x coordinate is going to change. The y coordinate stays the same. So we want to figure out how far is each x coordinate from -4. How many spaces away to -4? Just the x coordinates. Those are the distances, -4, -2, +2. If x equals -4 is right in the middle, we have to duplicate the same distance on the other side. So we take -4 minus another 4, -4 minus 2, -4 plus 2, and we get those new x coordinates. The y's don't change at all, so they stay exactly the same as they are. You can try the next example again. You can pause here. We'll have the answer show up in just a minute. Those should be the new prime coordinates. So now, instead of looking at specific lines, we're going to take a look at what to do with the axes. So that means the x-axis or the y-axis when we reflect over one of those. So we're going to reflect in the line y equals 0, which is actually a horizontal line versus a vertical line you'll see as x equals 0 in the next one. Y equals 0 is actually the x-axis, and x equals 0 is actually the y-axis. So they are a little bit backwards. You have to be careful about that. If you see y equals 0, think x-axis. The same strategies apply though. Figure out how far each point is from that line of reflection and duplicate it. Notice that point B in the first one is already on the line of reflection and it doesn't move. It's 0 distance away from the line of reflection. And if you're duplicating 0, it's still 0. So there are some shortcuts we can use. The x-axis, the x value actually stays the same. The y value changes signs. If you want to take a look at your graph that we just drew and take a look at the coordinates, compare them, you'll see that this pattern applies. For the y-axis, the y value stays the same, but the x changes. So taking a look at the y-axis, if the x was originally -2, the opposite of that is a +2. Same thing up here, if the y was originally a 5, the opposite is a -5. The difference comes with reflecting over the line y equals x. It's a normal linear equation, diagonal line with a positive slope, y-intercept of 0. You'll notice when you reflect across that line, the pre-image and image coordinates just flip-flop. The signs don't change, but they switch the order. So if your point was originally 2, 1, it's now 1, 2, backwards. This is the challenge problem. We have to write the equation of a line of reflection. It's important to remember that the line of reflection is a perpendicular bisector of the segment connecting points and primes. So to make sure we get the perpendicular factor, we have to look at the slope. To make sure we're using a bisector, we need to use the midpoint. Two different previous topics we have to connect. So we're going to find the rise over run to get from A to A prime. You're given the pre-image and the image. Well, a rise over run, we're going up 8 over 4. That's going to simplify to a -2. To get the perpendicular slope, we have to use the negative reciprocal of the original. We've talked about parallel and perpendicular slopes before. So instead of -2 over 1, we're going to take a slope of 1/2. Keeping that positive 1/2 over on the side, we need to find the midpoint. To write an equation of a line, we need a point and a slope. Right now we have a slope, now we need a point. So we want to take the midpoint, the average of the pre-image and image coordinates. That's going to get us 2, 5. Using that point, along with 1/2 for the slope, we're going to find the y-intercept and write the equation. So we'll use y equals mx plus b. This is the strategy I'll use. We're going to plug in 1/2 for x for m, 2 for x, 5 for y, since the point is x, y. So notice the colors. Notice where everything gets substituted. M for 1/2, x for 2, y for 5. And now we solve for b. We get the intercept by itself. 1/2 times 2 is 1. We subtract 1 from each side. We get b is 4. our equation is y equals 1/2 x plus 4. When this is graphed, the green line is what we just graphed. The black line is connecting A to A prime. You see that it is perpendicular, and these two sides are going to be the same. If you look at the rise over run, thinking about Pythagorean theorem, we're going up 1, 2, 3, 4 over 1, 2. Same thing will happen, up 1, 2, 3, 4 over 1, 2. Pythagorean theorem says those two distances will be equal, justifying that it's been bisected, the line segment A to A prime. Congratulations, you've made it this far. This should be the end of your notes.